Hello there. In this video, we'll be presenting about the Doppler effect. My name is Thammatara.
Hello, my name is Thapanawat.
Now, what is a Doppler effect? The phenomenon called the Doppler effect occurs when a sound source, like an ambulance siren, moves towards or away from a stationary listener. The Doppler effect is a change in frequency or pitch of the sound waves that reach the listener's ears. When the ambulance is approaching you, the sound waves are compressed and the frequency appears higher. Sound waves are bunched up because the distance between the source and the listener is decreasing. This causes an increase in the sound waves, or well, in the frequency of the sound waves, which makes the pitch of the siren sound higher. Conversely, as the ambulance moves away from you, the sound waves are stretched out and the frequency appears lower. The distance between the source and the listener increases, resulting in a decrease in frequency and a lower pitch. It's important to note that this effect is not exclusive to sound waves. It can also be observed with other waves, for example, light waves, which is why the colors of stars can appear to shift towards the red end of the spectrum if they're moving away from us, also known as redshift, or towards the blue end if they're moving towards us, also known as blue shift. The Doppler effect has several practical applications, such as in the Doppler radar systems used for weather forecasting, speed detection, and in medical imaging techniques like ultrasound. It's an important phenomenon to understand for anyone who works with sound waves or waves in general.
Redshift and blue shifts. The Doppler effect is demonstrated in many real-life situations, such as the buoy in the water. As the buoy moves through the water, it creates ripples that spread out in all directions. But if the buoy is stationary, these ripples will spread out equally in all directions. But if the buoy starts to move in one direction, the ripples will be compressed in front of the buoy and stretch out behind it, much like the sound waves from an ambulance siren. The compression and stretching of these waves creates a noticeable difference in frequency or wavelength, which in turn affects the perceived pitch of a sound. Similarly, in the case of light waves, if the source of a light is moving towards the observer, the wavelength of the light will decrease, resulting in a blue shift. Conversely, if the source of the light is moving away from the observer, the wavelength of the light will increase, resulting in a red shift. Redshifts and blue shifts are terms used to describe the apparent shift in the wavelength of light that is emitted by an object as it moves relative to the observer. Redshift occurs when an object is moving away from the observer, causing the light it emits to appear to have a longer wavelength. This means that the light is shifted towards the red end of the electromagnetic spectrum. Redshift is commonly observed in astronomy, where it is used to measure the distance and relative motions of objects in space. Blue shift, on the other hand, occurs when an object is moving towards the observer, causing the light it emits to have a shorter wavelength. This means that the light is shifted towards the blue end of the electromagnetic spectrum. Blue shifts can also be observed in astronomy, and it's used to measure the relative motions of objects such as stars and galaxies. The amount of redshifts or blue shifts observed is proportional to the speed at which the object is moving relative to the observer, and can be used to calculate the velocity of the object.
The Doppler effect states that when a sound source approaches or moves away from a person or object, the frequency of the sound wave changes. This is due to the fact that sound waves become bunched together or spread apart, as demonstrated in this visual. These two. So the sound source, S, is emitting a sound wave of 1,000 hertz. Since the sound wave is approaching person A, he experiences a higher frequency of 1,100 hertz because of the shorter wavelengths. And since the sound source is moving away from person B, they will experience a lower frequency of 900 hertz. This is because of the longer wavelength. This is to show that the wavelength works inversely to the frequency of the sound wave. When the wavelength is shorter, the frequency is higher. And when the wavelength is longer, the frequency is lower. So this is the formula for the Doppler effect. This formula is used to find the frequency that the observer is experiencing. So the formula begins with FO. FO is the frequency observed by the observer, equals to Fs. Fs is the frequency of the source multiplied by v. V is the speed of sound. Now, the speed of sound is not necessarily 343 meters per second. It actually changes depending on the temperature, but we'll get back into that later. Plus, minus, VO. VO is the speed of the observer over V plus minus, again, Vs. Vs is the speed of the source. Okay, so what I said about the speed of sound changing depending on the temperature has a formula that follows it. Okay, so it's V 301. 301 is the number or the speed of the sound at 0 degrees Celsius plus 0.6 T, T being the temperature and all of the air. So this is a formula used to find the speed of sound when you are given the temperature. However, if you're not given the temperature, you can assume that the temperature is T 20 degrees Celsius. So if you use T 20 degrees Celsius, you get 343 meters per second. So this will be the standard speed of sound if you aren't given the temperature of the air. So there are these plus minus signs on our formula here. And these plus minus signs change depending on our situation of our question, or we have to pick one depending on the situation of our question. So I have drawn out 4 possible situations that a question might pose for us. So the first one, this one right here, is where the sound source is moving towards us. Keep in mind that the speed of the source is a denominator, so we'll use a minus sign, because the lesser the denominator, the more value of the frequency. We want the frequency to be higher because the sound is moving towards us. This also is the same for our second depiction here, where we are moving closer to the sound source, so the frequency should be higher. So we'll be using a plus sign. Keep in mind once again that the speed of the observer is a numerator. So the greater the numerator, the greater the value of the fraction. Now for the two bottom here, we want the frequency to be lower. This is because both of these situations are moving away from the sound source, so the frequency will be lower. Okay, so for our third one here, the sound source is moving away from the observer. So we'll be using a plus sign because the greater the denominator, the less the value of the fraction decreases. And if the observer is walking away from the sound source, we'll be using a minus sign. This is because the lesser the numerator, the lesser the value of the fraction. Okay, let's do this example question I snagged off the internet. Okay, so it says, an ambulance truck emits a sound with a frequency of 800 hertz. 800 hertz. So we should write that down. I'm just going to draw it out. This is a sound source, and it's 800 hertz. So question A, which is what we're doing right now. Question A says that, what is the frequency detected by a stationary observer? Remember, stationary. If the ambulance truck is moving towards the observer at 30 meters per second. Okay, so keywords towards the observer and 30 meters per second. Okay, so let's draw that out. So the observer is here, and the truck is moving towards the observer at 30 meters per second. Okay, I'm just gonna write out the formula right here. FO equals FS V plus minus VO, oops, minus V plus minus VS. Okay, I'm just writing that really quickly, don't mind if it's messy. Okay, so since the sound source is moving towards the person, we want the frequency to be higher. And since the sound source is denominator, we will be using a minus sign to increase the frequency. So, okay, let's express this equation. So Fs, or the frequency of the sound, source of sound is 800 hertz, and the speed of sound v is 343, since there was no temperature mentioned in the question. Plus minus 0, since the observer, as mentioned before, is stationary. And then we get the speed of sound again, minus 30, because 30 is the speed that the sound source is moving towards the observer at. Okay, so we can simplify this to 800 multiplied by 343 over 313. Okay, so now just punch it into your calculator, and you will get a frequency. Oh, I should change that to squiggly. Okay, frequency of 877 hertz. So this will be your answer for A.
Other Doppler effect examples. The Doppler effect has a wide range of applications in various fields. Here are some examples. Radar technology. Doppler radar is used in meteorology to measure the velocity and directions of wind and storms. This technology can also detect the presence of objects such as aircraft, ships, and vehicles by analyzing the Doppler shift in radio waves reflected by the object. This makes it useful in air traffic control, weather forecasting, and military applications. Medical imaging. The Doppler effect is used in medical imaging techniques like ultrasound to study the movement of blood in the body. By measuring the frequency shift of the sound waves as they bounce off blood cells, doctors can diagnose conditions such as blood clots, arterial stenosis, and heart disease. Astronomy. The Doppler effect is also used in astronomy to study the movements of celestial objects. By analyzing the frequency shifts of light emitted by stars and galaxies, astronomers can calculate the velocity at which they are moving towards or away from us. This information can help us determine the distance, size, and composition of these objects.